Okay, so ladies and gentlemen, we're going to go through a whirlwind set of different presentations here. I wanted to talk about a topic that I really wondered about whether we should fold into it, and I decided that I would for several reasons. Number one, it bears significantly on the particulars of the areas we're talking about, particularly the combination of data science and system science technique, as a technique that can help address what I see as a significant roadblock for exploring the full potential of these techniques. The second is in the health sphere. It's a particularly central importance in my view. And there's great potential for applying this technique in a way that will help enable and in combination with the techniques we're talking about here. So I would argue that when it comes to combining data science with system science, because we're dealing with system science models that are by design integrative, meaning they are broad, they relate to many spheres of human activity. The data that we are using in conjunction with these models is often drawn from many spheres. It may be drawn from many sectors of society: social services, health, justice, education. And inasmuch as our models depict behavior at an individual level, as we might with an agent-based model, for example, there might be a desire to draw on data sets at an individual levels from across these spheres as they relate to single individuals in turn. So we might have cross-linked data from multiple spheres. And if one is to discuss this seriously, one has to grapple centrally and in a very decisive way with privacy concerns. There's very, very real privacy concerns if, in order to pursue a project, I need to access a person's health history and their criminal justice history, together with identifying information that allows me to join them. There's great concerns that can come out of this. So there's a very real question: how do we deliver on the full potential for combining data and system science while maintaining truly impeccable privacy guarantees? And I believe that achieving full and sustainable potential for use of big data in health, and I emphasize sustainable, not merely a flash in the pan, but something that sticks, requires a foremost emphasis on privacy preservation. I don't think it's a side issue. I don't think it's a speed bump in the road that we just got to navigate around. In fact, I think it's something we all have to, as a community, address centrally for us to have the public credibility and to have this be a sustainable enterprise. And I argued, it's the ability to link things cross-sectorally that provides some of the greatest insights for these methods, but the potential for conducting such linkages, as some questions during the boot camp revealed, is contingent upon achieving linkages in a manner that address privacy concerns by institutional ethics boards, institutional review boards, and others. As a society, we have to grapple with this issue. There are great benefits, but also great risks currently from operating with linked data sets. Now, within today's discussion here, I'm going to be briefly looking at one of several means of achieving this. Within the design of the SPPAL, we put a special emphasis on the sort of functional privacy architectures, whereby someone could send in a self-packaged, self-contained by virtue of containerization, self-sufficient sort of description of what of the computation one wants to perform, send it into an environment where the data is located, and have that data produced in a way that it's available in that environment rather than leaked outside. But my goal here is to talk about homomorphic encryption and to just give you a glimpse of this key technology. There There's also the opportunity for using synthetic data that I won't talk about, but which I think is also of central interest, particularly synthetic data which captures salient patterns, such as generated by a simulation model. So one need is to preserve privacy, have impeccable privacy guarantees while performing this sort of cross-sectoral analysis, something that we need to grapple with. A second major challenge is going to hit us even if we do not aspire to that. And it's the fact that traditional encryption tools that we've used for years, tools like RSA, the Ravesh, Shamir, and Edelman privacy preserving encryption technique, which is very widely used, are increasingly becoming vulnerable to the rising of a quantum computing infrastructure that is drawing closer and closer. And within recent years, partly because of that, there's been a growth of interest in what are called lattice-based encryption algorithms, I'm not going to define right now technically because of the limited time and limited relevance to the overall goals of this boot camp. But I will note that the techniques that I'm talking about here fall into the class of lattice-based algorithms that can be quantum resistant, quantum computing resistant, that can provide ongoing guarantees of privacy even in the context of a anticipated revolution in computing associated with quantum computation, which allows parallelization of computations at a high level. So the basic prospect of homomorphic encryption that I want to communicate to you is the fact that it has been demonstrated since work within the past decade that came out of Stanford University, but built on work prior to that, that we can separate, on the one hand, the need to access data in its full richness from, number two, the ability to analyze that data. Traditionally, if we wanted to analyze underlying data, we need access to it, to run our algorithms on that data. So those analyzing the data, involving identifying and other private information, are typically exposed to this information while they're conducting analyses. We may go into a secure infrastructure, such as that at Health Quality Council, for example, or that at the RDCs, the research data centers here on campus from StatsCan, and conduct information in that physically secure environment. But whilst in that environment, we may be exposed to identifying information that we carry with us in our heads, away from that environment in a way that could be detrimental to privacy. And this has traditionally been a problem because great analyses may come out of there that are merely aggregate in character in their findings, applying data science algorithms or what have you. But whilst in that environment, there's a risk to privacy, even if we don't take it away with any printed or photo or any other record. The very fact that I've been exposed potentially to what my neighbor's medical history is, or what my best friend's criminal justice history is troubling. It's a troubling thing. Now, homomorphic encryption addresses this and helps to unlink this traditionally fused nature that, look, if you want to do the analysis, you have to have access to that data. You have to have access and be exposed to this privacy concerning types of information. Homomorphic encryption, in short, allows an analyst to conduct analyses, potentially including the sort of analyses we're talking about this week. They could be implemented in theory in these sorts of systems on encrypted data. So what that means is I don't have to see the unencrypted data. As long as I have access to an encrypted form of data, I can run my algorithms on that. That's an important difference because whilst I'm applying them to the encrypted data, the need for high security is really minimal because if someone were to find that data, or if I were to look at it, I can't make heads or tails of it. Secondly, while I am working with it, I don't get exposed to these privacy concerns and privacy violations, to this information that I might inadvertently be exposed to about those in the society around me. So fully homomorphic encryption, in principle, permits arbitrary operations to be performed on the data. There's somewhat homomorphic encryption, where you can do certain things like total up numbers in a histogram or something like that. But fully homomorphic encryption which is what came out of the work at Stanford, the work of Craig Gentry, and has been extended in a series of important papers, is what allows you to do arbitrary analyses. And the analogy here that was advanced at a very nice thesis that came out of WPI on the subject, but actually was advanced by Craig Gentry prior to that, was the idea of a fume hood. So I don't know how many people have worked in a wet lab before in laboratory environments, but as I know from my wife's environment during her PhD, fume hoods are a big fixture of a lot of these environments. And the idea is you're working with toxic chemicals. You work on them in a safe zone where you're not exposed to them. And those toxic chemicals are placed into the fume hood. You can combine them in a way that could lead to production of toxic elements in the meantime. But because you're operating through gloves and merely looking at it through a viewing mirror, and because you're not actually touching the chemicals, you're not exposed to that. You're not exposed to these toxic elements. Just as for homomorphic encryption, you're not exposed to the privacy, to the revealing elements. And you can perform all your operations in the safe environment without any risk to yourself in a way that is totally protective but allows you to get the job done. And so it is with homomorphic encryption. So if we want to operate on the data, and I'm showing it here as a function of the data, we want to engage in some search of the data and count the number of things which have a certain characteristic, for example. It turns out that we can apply that same basic method on the encrypted data and get back the same answer. But there's a difference. There's a difference between what we get back if we just immediately apply it to the unencrypted data, or apply its encrypted analog in this homomorphic domain, this version of F that operates on encrypted data to the encrypted data. The difference is, applying these encrypted one, we get back an encrypted result. Now think about that. So maybe I want to count the number of individuals. I want to do a histogram of the number of past occurrences of offending in a certain population, and break it down by age categories, or break it down by some aspects of background. I can go in and work and see I have the encrypted data. I can't make heads or tails of it. It's gibberish to me. And I can run this algorithm on it that computes a result. But the result isn't the histogram. The result is an encrypted version of the histogram that needs to be okayed before I see it. It needs to be okayed by a trusted party who does have access to that data and can say, okay, this is acceptable, it's released to you. But I could perform the full encrypted algorithm and be aware if it succeeded or not in a way that might allow me to speed up my work compared to if every time I needed to ask someone else to undertake it. So the above yields a result that is itself encrypted. The difference from applying it normally is I'm working on the encrypted data. So I don't see any information about my neighbor that I can make sense of. I don't know that there's anything about my neighbor in there. There might be, but I can't see it because it's all gibberish. It's all Greek to me. It's all encrypted data, and I get back this encrypted result. Now, the basic way in which this occurs, and it's a very clever way, well, maybe I'll mention two applications, and we'll come back to this. So two modes of computing with this have great significance. One is, look, there's some party that has legitimate access to this data. But they're wary of having analysts, such as myself or others, come in and analyze that data by looking at the underlying data directly. Okay, and basically the idea here is, okay, I don't know what happened here. Something. The idea with the data analysis is, I want to come in, or that data can be provided to me in an encrypted form. I can analyze it. I get back an encrypted result, and I ask the gatekeepers, can I see this result? And they will take a look at it. They will decrypt it. And they say, yeah, that looks, there's no small cells here. There are no concerns about this. Here you go. They might also ask to see my query, right? So they know what am I seeking to compute in some cases. But the point is, they provide a gatekeeper role in giving me back the results that I need to see the final result, and I can't see it until they give that go-ahead. The second, again, apologies for this. With utility, the other way that this could operate is with utility computing. The idea here is the following. I'm the owner of the data. Maybe I'm the Saskatoon Police Service, or maybe I'm Social Services, maybe I'm Ministry of Health. There are certain computations that need to take place in this data for my needs. But maybe I want to perform those computations in the cloud. Right now, that's a dangerous proposition. If I put data from social services out on the cloud, or from health, from the Ministry of Health out on the cloud, how do I know there's not going to be snooping involved? The person who backs it up is not going to look at the data. The custodians out there won't look at it. It's out there in the cloud. Maybe it could be broken into. Maybe it could be hacked and someone could steal that data. That's a troubling proposition that prevents a lot of organizations which have private data from taking use of infrastructure provided by utility computing groups like Amazon Web Services or Google Cloud or other similar platforms. And it's very troubling because it means they have to maintain often somewhat cumbersomely computing infrastructure within their organization that often doesn't compare with what could be obtained out in the cloud. So how does homomorphic encryption address this? Well, if you put data out in the cloud, normally, in an unencrypted way, people could see it, it could be hacked, bad things could happen. But if you encrypt it with homomorphic encryption, you can put it out in the cloud and then perform the computations in the cloud on the encrypted data. Because those computations are taking place on the encrypted data, even if the system were hacked, the encrypted data would be unintelligible. The results that are computed are themselves encrypted, so anyone who found them wouldn't be able to make sense of it. The results can be provided back to me and I can decrypt them. And I can have the answer as the owner of that data. So here, with utility computing, it allows me, as an organization that has private data, maybe it's the SPPAL, to take a lot of that computation that would go in within closed doors within that facility, put it out there for high performance utility computing vendors to perform, but with total confidence of maintaining the privacy because everything is encrypted, all the results are encrypted, and no one can make heads or tails of the data, even if it were hacked or if a wayward system administrator were to peek at it before doing the backup. That is the prospect here. And it provides a certain flexibility. It provides a flexibility in terms of where you do your computations, and it provides a flexibility in terms of allowing people to come in who don't rightfully, aren't fully trusted with all elements of the data. So how is this achieved? Well, for those students of mine from my lab, I've shared with some of you very detailed characterization at a mathematical level of how this is achieved. But the basic idea is as following. If I encrypt some data and I get a result out, traditionally, I encrypt a number 0 and I get a defined result that corresponds to 0. It's 0 in this other domain. Or I encrypt a name and I get an encrypted version of that name. That's a problem traditionally because I might be able to figure out what that was by comparing it with the results of other encryption. And if I can perform computations on it, I can look for an element, I could add to things, which gives the same result, and I say, that's my 0. And I can work up from there. So what happens with a fully homomorphic encryption is actually, you encrypt, but you add noise. You actually add noise to the result. So there ain't no unique encryption of 0. It can encrypt to many different things, and I can't figure out which of them is the 0 because there's no unique one. And noise keeps on being added, but it's kept within certain bounds so that there's absolutely no ambiguity when you decrypt it that you'll get anything but the original thing. And noise builds up, and then there's a noise reduction process. But noise builds up in an encrypted domain, in the encrypted items. And then we perform a noise reduction process that reduces it. So at all times, while noise has been added, the person who has the real key for it, the trusted gatekeeper, they can decrypt it and get the full results back. They can decrypt it and get the results back. And what's going on beneath the surface is there's a lattice defined by polynomials using modulo arithmetic, and it's beautiful mathematics involving rings and ideals, elements of group theory and ring theory and number theory that I have no intention to going into on a Friday afternoon following lunch. But it's beautiful. And I hope someday some of my students will come sit as Winchell and Jason have. So what are some disadvantages of this? This seems to open the door to profound analysis. Imagine if we could apply all the techniques we're talking about here to linked data from multiple ministries that can be provided to researchers or others with no risk to privacy, and still allow analyses to take place in them and to be checked for suitability for release by trusted parties. This sounds very, very attractive. What are the disadvantages? Well, one is it's more computationally expensive to perform operations. Something that requires, an hour for me alone in terms of getting the result back for issuing a query might take several hours on the encrypted data. Much higher storage costs. So the encrypted data takes more space to store. And it's related to this issue of noise and needing to keep multiple keys because keys are rotated, associated with getting rid of noise, etc. You need right now to write more complex code for performing the analysis, and that slows learning and it's higher amounts of human time. We're going to be working to address that. And you need for a trusted party to decrypt the data. You need the equivalent of Don Elliott to sort of say, yeah, thumbs up, this is a suitable result for you to see, or a lab manager who is a trusted party. It takes away the risk that the analysts see the data, but there needs to be a trusted party who can decrypt it if you have this model of a gated access. And finally, there's some issues with conditional computations where you're asking, is this the same as that pose some additional challenges with in terms of analysis. So our own inclination when working with these approaches, which are at a practical sphere, we are applying them in our lab at a small scale right now, is use fully homomorphic encryption for subsets of data, such as identifying information and high-risk information, for cross-linked data, And you can use approximations to homomorphic encryption, such as with the database system known as CryptDB, which is an open source system that came out of MIT, my old lab, that does support this sort of mechanism in a ready-to-deploy type fashion. And you can use somewhat homomorphic encryption, which is faster for certain types of operations. So those are all my comments here on homomorphic encryption. I just wanted to communicate to address one of the questions that came up earlier in this boot camp, and to address a question that might have been on many of your minds, which is, okay, it seems that we have the analytic tools, system science models, capacity to take in multiple types of data sets to illuminate broad areas of a system, broad areas of a person's life based on data from multiple sectors. It all sounds great, but at the end of the day, some of the people in the room here know even better than me the challenges associated with getting those data sharing agreements signed. Getting that final signature from those ethics boards to sign off on data that crosses sectoral boundaries. Breaking down those traditional silos of resistance to releasing information to other organizations, with the sense that data is power sometimes, and giving up that data is vulnerability and can be criticized. Jeff told me early on, when I wore a younger man's shoes, that data is often guarded fiercely for political reasons, and often is jealously protected. And one of the big reasons, which is perfectly legitimate, is concerns that there'll be security violations, privacy violations that will cause everyone to have egg on their face from the minister level on down. If we can provide approaches which literally provide these sorts of system science approaches combined with data science, this rich data cross-sectorally with integrative models to perform their analytics in a context where privacy is given foremost preeminence, where there's essentially no risk to individuals because the data has been handled in an encrypted fashion, which has foremost emphasis on making sure that even hackers or other adverse parties among the analysts can analyze it, can reveal it. We have that chance of moving beyond some of these constraints, some of these concerns. And that's one of the reasons why I've started to do some work very seriously in this area. It's to enable these techniques to go further and reach their potential by addressing these privacy concerns that so often limit the breadth of their application because of very real and important and central concerns as to privacy risks. So that's a glimpse of homomorphic encryption. It's a totally different topic than we focused on during the week, and one that I didn't want to go into in detail, but one which, if you think about looking forward, if you think about the glimpses of techniques you've seen, this may be another reason for great optimism about the potential of these sorts of methods in the medium and longer term, and hopefully with our efforts, perhaps even in the short term. Okay, so that's homomorphic encryption in a nutshell as it relates to this week's goals. While I switch over to